So, let's move on to Ashley. So, Ashley here is from is Haitian and American, originally from New York, but also from Baltimore, which she tells me is pronounced Baltimore. Did I get it right? Nice. And she works at MD Logics, and they do work to help people with chronic pains and stuff like that. Is that correct?
Chronic care management.
Chronic care
management.
management.
We'll get into it. Don't worry.
Sorry, I got
okay.
it wrong. But she is a wonderful person. I'm very excited to introduce her to you, and please give a warm welcome to Ashley.
Yes, thank you. Hello, folks. The title of my talk today is A Gentle Introduction to Tree Data Structure, with a key emphasis on the gentle. A little bit about myself. I'm from the US, and I work as a Ruby developer for a company called MD Logics, based in Baltimore, Maryland. Our company creates applications surrounding behavioral health integration and chronic care management. Also, I am a part-time graduate student at Towson University studying computer science. Before we begin, just out of curiosity, how many people learned how to code the traditional way? So majoring or studying in computer science in an academic setting. Can we get a show of hands? Okay, wow. Okay, you can put them down. So with that being said, now how many people learned how to code in non-traditional ways? So boot camp, self-taught, etc. Awesome, awesome. Okay, so now how many people understand trees and data structures? Okay, cool. That's good. We have a very educated crowd here. Okay, so now here's the kicker. Now how many people know trees only for the purpose of tackling interview questions? Yeah, yeah, I hear that. Well, that's great. Thanks everyone for participating. I asked these questions because I wanted to highlight the differences in our experience amongst conference attendees, and also to show that sometimes data structures can be still an iffy subject to get our head around. For me personally, when I took an pause. Okay, so for me personally, when I took an advanced data structure course last fall, my emotions were incredibly similar to this GIF. One day I would be really confident about the material we were learning, and then I would get a pop quiz. And then I realized, nope, I don't got it, back to the drawing board. So with that being said, computer science fundamentals can sometimes take some time to wrap your head around, but just like anything else, in due time, you'll reach your goals. So in the next 30 minutes, we'll discuss why trees are useful, the fundamentals of commonly used trees, and their properties. More importantly, throughout the presentation, I'll provide examples of trees to show you how they're relevant in our code. For folks familiar to these concepts, which was half the room, let this talk serve as a review. And for folks new to this material, I hope this talk serves as an exposure and ultimately a foundation for which you could build upon. When it comes to data structures, we have many types to choose from. We have what's called linear structures, such as an array and a linked list. In a linear structure, every item is related to its previous and next item. We also have what's called a nonlinear data structure, such as trees and graphs. In a nonlinear data structure, every item is attached to many other items. Typically, depending on the data, we use a certain type of data structure. So let's start with what is a tree exactly. A tree manages data in a hierarchical way. Take, for example, a family tree, a famous one, The Simpsons. The grandparents are at the top, followed by parents, Homer and Marge, and the children are at the bottom, Bart, Lisa, and others. Each family member are displayed accordingly and can be easily accessed. Okay, so now this is a long definition, but I wanted to point this out. So this is from my data structures algorithm book. So a tree is a collection of nodes. The collection can be empty, otherwise a tree consists of a distinguished node called the root. and 0 or more non-empty subtrees. Each of those roots are connected by a directed edge from R. I remember in class reading this for the first time and saying, what does this even mean? So I know it sounds a little long-winded, so I wanted to break it down a bit. Let's focus on these 4 keywords: nodes, root node, edges, and subtrees. So in a tree, we want to look at it as if it's upside down. We start with a node. A node is simply an object that contains data. When creating a tree, we start with a root node. A root node is at the top of the tree, and every element at the root is trickled down. Nodes are connected to what are defined as edges. A root node can be followed by another node. If a root node is connected to another node or nodes, the root node becomes a parent of those nodes. In other words, the yellow node is the parent to those red nodes. Similarly, children nodes are the nodes below the parent. So the blue nodes are children nodes of the red nodes. Plot twist. In this example, the 2 red nodes are known as sibling nodes as well because they're on the same hierarchical level. We also have what's called subtrees. A subtree is a portion of a tree data structure that can be viewed as a complete tree in itself. So under the root node, we have a left and a right subtree. Other things worth mentioning: leaf nodes are known as the last nodes in our tree. It's the node that doesn't have a child node attached to it. So now time for some calculations. The depth of a node is equal to the length of a path from the root to that node. And the height of a node is the longest path from X to a leaf node. Lastly, the number of edges is calculated by the number of nodes in that path subtracted by 1. So in this case, we are looking at the edges on the right-hand side. We have 4 nodes, and 4 minus 1 is 3, so that gives us 3 edges. Next up, why should we use trees? Well, trees are great for storing naturally hierarchical data, organizing data for quick search, and inserting/deleting nodes in moderate time. Here are some examples that you might be familiar with. A filing system. It consists of files and directories. We start at the root and folders are broken down. Each directory contains a set of files and directories. Root to user, user to me, Ashley, then Ashley folder to desktop and movies. The DOM is another example. The DOM is a representation of your HTML to the browser and allows you to manipulate the page. It's a tree because the DOM starts with a single parent item that branches out into children items. Children items are branched out into smaller trees. Again, we refer to those smaller trees as subtrees. Okay, great. Trees are all around us. We use them pretty frequently without knowing. Big whoop. But why should we actually care? So this is where we bring up performance. The runtime of using a tree tends to be a lot faster than other data structures, especially when executing certain operations. For folks who may not know, runtime is defined as the time during which a program is running. We can measure that time using what's known as Big O notation. For a quick definition, Big O notation is the language we use when talking about how long an algorithm takes to run. Big O is calculating using logarithm equations. We usually describe Big O at the worst case scenario. In other words, the question we're asking ourselves here is how long will it take for my algorithm to run in the worst case? In this graph, the best Best worst case scenario, that's a doozy. Best worst case scenario for a runtime is a shade of darker green at the very bottom. That is O log n and constant time. So green for excellent, which is awesome. That's the dream for an algorithm. And incrementally, the worst case scenario gets, well, worse. It goes from excellent to good, then fair at yellow, then bad at orange, then horrible at reddish pink. So the absolute worst case scenario for runtime would be n factorial. I know some of you are probably asking, why the heck am I talking about logarithms when I'm supposed to be talking about trees? But stay with me, it will make sense. I just needed to give you some information for the upcoming slide. Now let's compare some data structures. For the first two data structures, let's hypothetically say that our data set is on the smaller side. So remember that phrase for later, smaller size data sets. Okay. The first one up is an array. To search an array, the runtime would be O of 1. Because we would need to iterate through the elements, that would be the same for the remover process. We would need to find the elements that we are trying to remove. Okay, so now let's say we have space for a new element. That would give us a runtime of constant, so O of 1. We can say that the runtime for an array is pretty good for those three functions. Next is a linked list. So similarly to an array, the runtime for linked lists, searching and inserting and removing an element would be the same, with O of 1 and constant time. So with these incredible runtimes, I mean, what's the point of ever choosing another data structure? I mean, according to the big O notation graph we looked at earlier, our runtime for an array and a linked list is on a good mark. So no need to worry about performance. But wait, remember the key word I mentioned. The data sets are on the smaller side. So what happens if the data sets increase? Well, it would take longer to run those data sets. So it wouldn't be the same runtime as we've illustrated. Now the question is, how do we make this faster? And this is where trees come in. Let's say we're looking at a binary search tree, something we'll go over in later slides. We can perform a binary search tree by sorting it in an array. Using a sorted array. Now let's say we're looking to insert a number into an existing array. The binary search will look for numbers greater than that specific number and insert the number in the correct place, cutting the work essentially in half, and that will lead to better performance. The average binary search runtime for search, insert, and deletion will be O log n. Thus, using a binary search will be faster and better than, let's say, an array or a linked list. The next tree we will examine today is a binary tree. A binary tree is a tree in which each node can have at most 2 children. Here are some examples. The first one, weird if you ask me, but it's a binary tree nonetheless. Remember, a node doesn't necessarily have to have children. Within this case, each node has 1 child node. Finally, in the last one, the root node has 2 children, and that's the maximum a binary tree can have. And each red node has 1 child. To add to this, let's look at what we call a binary search tree. The proper definition of a binary search tree is defined as a binary search tree where values of all the nodes in the left subtree is lesser than all the nodes in the right subtree. Binary search tree are elements broken down into smaller pieces that are still connected. As we mentioned, in a binary search, the left subtree is lesser than the right subtree values. The left subtree will have values less or equal to its parent node, and the right subtree will have greater or equal to values to that parent node. So let's take a look at how a binary search looks like when it's created. 21 is our root node. Then the tree inserts numbers greater than 21 on the right-hand side. So 28, 32, 25, etc. And to the left of 21, the smaller numbers are placed. So 14, 11, and 18. I realize it's repeating. So if we look at this again, I think what I always thought was interesting about binary search trees is that when you insert a new node, it automatically becomes the leaf node. So, yeah. Now that we've discussed the creation of trees, let's briefly talk about tree traversals. This is a process we take to visit all the nodes of a tree and to print out their values if we'd like. Now, tree traversals is a topic covered extensively when it comes to trees, and to be honest, it could take another hour to cover, and we all have a party to attend to. So I won't have time for that today, but I just wanted to keep it brief. So if you look at this animation, there are 4 types of tree traversals. There's pre-order, in-order, post-order, and breadth-first search. Essentially, each traversal starts and moves a certain direction. One moves to the left subtree first, while the other traversal starts at the right, and etc. Thus, these 4 options allow various ways to access each node in a tree. Now, moving back to our examples. The most common example of the usage of a binary tree is, well, searching. Let's take a dictionary. And let's say we're looking for a word like Ruby. So typically, if we were looking for a word, we would kind of gauge to where to start. So towards the middle, end, or somewhere else. So for Ruby, it starts with an R, so we have a hunch that it would start from the middle to the end. We'll flip to that section, and once we're there, we'll guess again to see where the word would be. And each of those guesses will lead us closer to the word. And we'll find the word we are looking for quicker because we're splitting the sections in half each time. A search algorithm in binary search will do the same thing. For this example, let's say we are a health organization trying to search for a participant's name and personal information. We need to retrieve that data from the database. But how? Well, a database uses indexing to search for the correct row to retrieve and return that data. With binary search, it's able to search for the correct index. B-tree is another type of binary tree that is super efficient for storing data in an indexed database. Essentially, you could have more than 2 nodes. And they handle large amount of data in ways other trees might not be able to, because they can handle data that cannot fit in memory, in the main memory rather. To search for a participant, it will start from the root and recursively traverse the tree from top to bottom until it finds the given node. At each level, the search reduces the clutter of unnecessary indexes and only keeps those in the range of the search value. Once it's found the index, it can return the patient's name and information. This is why in nature, a binary search tree is a recursive data structure. We divide the work into half many times until we find our data. In computer science, this is referred to as divide and conquer. Now it's time to see how binary search trees translate to Ruby code. So in Ruby, we would initialize a node. The variables we care about is the value in which the node will carry and what's it pointing to. So that would be the left and the right of the node if there is any. We also want to set up the root node, since it's the specialized node that indicates where the tree starts. So to insert a value into the root, we will need to check if the node is nil. And if it is, the root node will be created with that value. If it's not nil, then the value is moved to the insert function, where the value will be delegated. With that new value, we compare it with the value we already stored. If the new value is less than or equal to, it will be placed in the left subtree. We then use a ternary operator to further check the value. For folks unfamiliar with this operator, think of it as a shorthand compact if statement. If you want to see if the left subtree is nil, so in other words, does it have values already in it? If it doesn't, then the new value will become a part of the left subtree. If the left variable is not nil, then we will insert the new node in the left subtree. But we'll have to use the insert method again to verify if the new value will be in the appropriate place in the left subtree. We will do this again in the right, so in other words, if the new value is greater, then our existing value will do the same comparison. Now, this is a fun part. What do we do if we want to search a node? Again, we use a recursive approach to traverse the tree. We are splitting the search in half each time. We compare the values with the existing value in the tree. And if the value is less than the existing value, then we use the search function again to repeat those steps. Again, this is the same if the value is greater. Once the node is found, we return the value. These are the results that we would produce if we were like making a tree. So I printed a tree for us. So as you can see, the root node is nil, followed by the smaller values on the left-hand side. So 6 and 3. And since 3 is a leaf node, there's no left or right value, so it's nil. 8 is on the right subtree of 6, followed by 10. Again, since 10 is a leaf node, so there's no left or right values. On the right-hand side of the root node, 11, we have values 16, 32, and 32 is a leaf node, again. So great, we've gone through trees, we've seen some examples, we've learned about their benefits. I guess the talk is over, right? But if anyone remembers, are the people that know trees, you're not quite done because binary search trees only work best when the tree is balanced. So yeah, there's that. Remember this fun graph? Remember, it's all about runtime, the performance of our algorithm. Well, if our tree is not balanced, our average runtime would not be the same. It would become worse and would become O of n, which would put us at a fair runtime. Here's what a non-balanced tree versus a balanced tree looks like. Looking for something in an unbalanced tree is like looking for a word in a dictionary page by page, and no one wants to do that. So we need to find a faster way to do that. We need to find a way to balance our tree. Thankfully, we have what's called self-balancing trees. The first one is what we call an AVL tree, and that's done through a series of rotations. In the most simple explanation, an AVL tree checks the height of the tree. The difference between the depth of the right and the left subtree cannot be more than 1. And if the height is too large, it will complete a right and or left rotation until the tree is at a balanced height. The second one is known as a splay tree, and this is another type of self-adjusting tree. So this splay tree tends to be useful for implementing caches and garbage collecting algorithms. This structure gets organized as the nodes are accessed. Every time a node is accessed in a splay tree, it is moved to the root of the tree. So this also ensures that the tree is balanced at each point of access. So B tree is also a self-balancing tree. The height of the tree is automatically adjusted on each update in order to keep it evenly balanced. There's so many other trees too. like heaps, tries, red and black trees, spanning trees, and the list goes on. So this doesn't have to stop here. Now that you've refreshed or learned some fundamentals on data structures, go forth and continue learning. So let's recap. Trees are great for storing naturally hierarchical data, organizing data for quick search, inserting/deleting keys in moderate time. Binary trees have at most 2 children. In binary search, the left subtree is lesser than all the nodes in the right subtree. Traversals is a process we take to visit all the nodes of a tree to print their values. B-tree is a self-balancing binary search tree that can have more than 2 nodes. It handles data that cannot fit in main memory. And the examples we covered today were family tree, HTML DOM, database indexes, implementing caches, and general database searches. Here's some Ashley approved, as I like to call, resources I'd recommend if you're interested in learning more about trees or the data structures and algorithms. There's a podcast I really love, a YouTube series, visualization, and some books. I'll be posting these all online too. And here's some resources. So that concludes my talk. Thanks, everyone. If you have any questions, I'll be in the speaker lounge.
Well, thank you very much.
Thank you.
Oh, yes, we have a small present for you. Sorry.
Oh, okay.
Yes? I hope we can leave you with something nice.
Oh, thank you.
I love the groans. Thank you.
Yes.